Okay. So I'm Jared Parsons, and I'm here to tell you about the System C# programming language. I am going to try to leave some time at the end for questions, so if you could please hold them to the end. I'm going to try to get about 10 minutes for questions. So the System C# language originated from Midori. For those who aren't familiar, Midori is a ground-up operating system effort written in C#. And even though it's written in C#, this is actually, it compiles down to native. We do not run managed code. So we compile directly to ARM, x86, or AMD 64, and we run directly on the hardware. Midori is based on the principles of correct by construction, non-blocking API calls, and we really embraced rigorous static analysis right from the get-go. At the beginning, though, we did this with fxcop. And so we had hundreds of fxcop rules to enforce things from values which couldn't appear on the heap because they are dangerous, to our data contracts must be immutable, so only use these safe, blessed set of types, and enforcing things like our exception model. And we very quickly reached the limits of what you can do with fxcop. For one, it's just too easy to suppress. Any developer can violate the type system with a suppressed message attribute, and that's just broken. Generics were always a problem because people writing fxcop rules are not necessarily compiler developers and don't necessarily understand generics. And we often bring in old code bases into our system, and porting fxcop to that was just not always a good idea. When we stepped back and kind of looked at what we were fundamentally trying to solve, we realized this, we're trying to build a type system here. fxcop is not meant to build a type system. So about that point, we decided that it was time to invest in some language changes. We kicked off, we really wanted to build a type system that is universally and ruthlessly enforced in our code base. We kicked off M# in about 2010. We started the C# 4.0 compiler code base. Sometime later, we merged with 5. In the beginning, we started off with some kind of easy-to-hit, low-hanging fruit features. We implemented awaits a little bit before the C# team did, ref returns, ref locals, things of that nature. And as time went on and became more comfortable, we started moving on to our bigger features: immutability, contracts, error models, destruction, all the good stuff. This year, we decided to kind of take the next step and move on from a code name to our more official name of System C#, and so we've been embracing that name this year. If you look back at some of our old docs, you'll see M# littered everywhere, but it's the same language. So the philosophy of System C# is we are to C# what C++ is to C. We want to embrace evolution here, not revolution. The basic design principles are, number one, do not break back compat with C# unless we absolutely have to. We want our features to be completely separate and be able to be adopted incrementally. We always prefer explicit over implicit. This is going back to our philosophy of correct by construction, very readable. And we want C++ code quality with a C# productivity. So we do compile down the native, and we want our native code to look as good as C++. And the advantages of this philosophy is C# developers can code System C# today. When we bring a new developer into the Midori team, we don't say, hey, here's this great operating system, this great language. We'll see you in a month when you've learned it. We say, no, just bring what you know today and start using it. As you get more comfortable with the language, you can adapt these features and make yourself even more productive. Our back compat breaks are really small, and the majority of them are controllable with a compiler flag that does not violate our type system. So it's very easy for us to adopt developers and old code bases into the Midori system today. So the first thing I want to talk about in terms of features is destructible and borrowed. So this is some code taken pretty much directly from our MIME multiform parser. And this illustrates a lot of the problems that we were having with ownership in our system. So the first question we look at this is just a basic parse method that's parsing out the header of a MIME packet. And the first thing we have to ask ourselves is, hey, there's a stream type up here. Is that a disposable type? Is that something that I need to be aware of? You know, you have to go inspect some source code to see whether or not that's disposable. It is. And the next question you have to ask yourself is, do I dispose this type? Did the guy who gave it to me, is he going to dispose it? How do I know what the contract is here? You look around, you'll figure out probably not my responsibility. And another problem we have is there's actually two disposable types here. We have stream and we have buffer. Buffer is this really neat little thing we have to safely allocate some native memory so that we don't have to pollute the GC heap to get an array. So we allocate this buffer, we keep the native guy around, And we use this span type to kind of access it. And the problem here is span is kind of tied to buffer. It's accessing this allocated memory. And if we do something dumb like return span up the stack, we've got a dangling pointer. We have to have runtime enforcement or some other kind of horrible thing to do. It's generally not well. The other problem is we have to double dispose this value. Because buffer is both assigned to in the peak method and it can potentially be left with an exception, we end up having to have all this double dispose logic. And also we have all of this ceremony around managing these resources. And generally it's pretty painful. It requires a lot of code inspection, and it's not terribly easy for the casual person to review this code. You have to know a lot about the semantics of these types. So our solution is basically to start by encoding ownership into the type system. Make ownership and use cases explicit. The way we represent the use, we basically have this thing we now call borrowed values, and it represents the use but don't store mantra. I'm going to give you this type. You can use it. You can use this list, clear it, add it, do whatever you want, but you cannot hold on to this list. You must give it back to me when you are done. This is heavily inspired by C++ references and Rust borrowed pointers. And as such, we are using the ampersand syntax to signify this. And what this does is it provides definitive lifetime information to the compiler. Methods which take borrowed parameters can't stash them away. They can do whatever they want with them for the lifetime, but when that method exits, they cannot hold any long-term references to those parameters. And also, if you allocate a borrowed parameter into a local, that value cannot escape up the stack. It is guaranteed to be bound to the place that we allocate it. And immediately what that gives us is stack allocation in the language. If we know where it's allocated, we know it can't go any higher, and we know no one can hold on to that guy. Hence, we can take all of these little temporary things that are polluting all of your stack frames in C#, and we can put them straight onto the stack. We don't pollute the GC heap. It's really awesome. And in combination with that, we also have introduced destructible types into the language. We've gone through a couple of iterations of this, and the one we've settled on is heavily inspired by C++ 11 smart pointers. So the idea is ownership is explicit. We have owned types, which is essentially, it's very similar to unique pointer in C++. I have a single value and a single owner. When this value goes out of scope, foo is destructed unconditionally. Then we have share types, which is there are one value with many owners, and each one of them equally basically has a ref count under the hood. And as they leave scope, they're going to decrement the ref count. When the last guy goes out of scope, we're going to nuke the value. And the third one is a borrowed value. So what we're saying here is you can use foo. Foo is guaranteed to be alive as long as these borrowed values are here. You can use it, you can read from it, you can write to it, but you cannot destruct it, and the person who owns it also cannot destruct it. The compiler will enforce at compile time that for any borrowed reference, the destructible value will be alive for the lifetime of that reference, and transitively any other borrowed reference which points to it. And what this means is our destruction safety is enforced at compile time. We don't end up with any dangling pointers in our system. And so if we go back to this original example and look at it in our new model, first off, you can see the try-finallys are gone. And right off the bat, the ownership of this stream class is now explicit. It is explicitly stating that I'm just using the stream class. Someone else is responsible for creating and maintaining that reference throughout the lifetime of this method. And also, this other disposable type is no longer just hiding in the system. It is now explicitly said that I'm a destructible type, they are shared ownership, and I am one of these owners. And one of the nice things is we got rid of that horrible little span type. That span type that used to be there to protect ourselves from dangling pointers and all kinds of other runtime implementations is gone. We can directly reference the byte array here because we've now said that it's borrowed. It's dependent upon this buffer type, which means it cannot escape up the stack further than buffer. There is no possibility of a dangling pointer here, and it's just a plain old array like everyone is used to seeing. And the other benefit here is we have all this automatic destruction. Buffer will be destructed as the scope's end. The user doesn't have to do anything special. There's no need for usings, try-finallys. The code is much cleaner here and is now much more focused on the actual algorithm instead of all of the resource management that comes with it. So another big thing that we've done in System C# is what we call taming side effects, or TSE for short. Our main motivation here is that APIs today have tons of implicit side effects about their data. APIs have, say, basically, for instance, they want you to be able to read from my data but don't write to it. Or while I'm running, the caller can't write to my data. For instance, while the sort method on list of T is running, it'd be really bad if the caller decided to do things like clear the list or add items. It'd kind of break the sort method. And we have all of these other constructs, like methods must be pure. If you have a code which executes in a debug.assert, an if-def debug, or things like that, it's really important that they don't mutate state. Otherwise, when you compile your code in release mode, you're going to get different semantics. And this is all throughout the code base. And unfortunately, none of these things are enforced. There's no way to enforce them today, really. The only things you can really do is, if you don't want people to mutate your collection, you can allocate another object and pass it, like read-only collection. You can pass enumerable, but then they could just cast it back to list of T and clear you for fun. You can also use some strongly worded comments. Those are somewhat effective. And these problems are just magnified when you put concurrency in the picture as well. So the way that we've addressed this problem is that we've added permissions into the system, essentially ways of restricting what you can do with an object. The permission everyone should be familiar with is writable. It's the unstated permission. You can state it if you want to. It's implicit. But it gives you exactly what C# gives you today. You can do whatever you want with that object. Readable, though, means that through this particular reference, you cannot mutate this object or the transitive set of closures which are reachable from this method. It is a way of pure inspection of values. Now, someone else could have another reference. You could have a readable list and a writable list that point to the same thing. So someone could clear it out from under you. But through that one reference, you can do no harm. Immutable is basically a way of saying there is no writable references to this object anywhere. It can only be inspected from here on out. And since this is a full part of our type system, we do have parametric polymorphism. You can have generic permissions. They do flow through the language. It's much more of an advanced scenario, and pretty much no user code ever uses it. It's pretty much reserved from interesting library calls, but it does exist, and it does work pretty nice. The way we've modeled these is just subtyping relationships. The top type in our system is not object. The top type is actually readable object. And writable and immutable can both convert to readable. No allocations needed or runtime enforcement. It's just a nice little subclass relationship. So permissions can go on values, parameters, members, what have you. And here's a simple example of applying readable to a getter. We have a person class here. It has a name and a nice little getter and a setter, and the getter is marked as readable. And what this means is we cannot do things like assign to fields. That will be flagged as an error because that's a mutation. We cannot call methods which themselves transitively mutate the object. For the same reason, it's writable, and a readable object can't call writable methods. We can, however, do inspection. We can return values out of that object just fine. And the exact same restrictions come from uses of that object, because here you see we have a person instance which is readable. We can call the getName method, no problem. But if we try to do mutating operations, the compiler smack you down and say, bad boy. And what's great about the system is because we've actually really ingrained into the type system, we can use it in generics as well. It's not just limited to objects, just non-generic objects. So first off, we're going to start with a deeply writable list. So I can do things. I can add to this list. I can grab elements out of it and mutate them, no problem. What I can also do is I can assign it to a deeply readable list. And what this is saying is in this list, I can't call methods that would mutate the list, and I can't do things which would mutate elements of the list. It's readable. It's an inspection-only system. And you notice this is just an assignment up here. There's no runtime enforcement. This is all a part of our type system. It all just flows. But what we can also do is we can have shallow readability in our system. We can say, hey, I want to give you a list. You can't add or remove elements from it, but you're free to mutate the objects which are inside of it. And so it's a readable list of writable person objects. And once again, this is just a simple assignment. It flows out from our type system, no allocations, no runtime enforcement. And with this, it'll properly guard calls which attempt to mutate the list. But if you want to mutate the elements of the list, That's fine. You can grab them out and change their names. Now, one other thing we kind of haven't covered is immutability. So our type system does support the idea of immutable types, which C# has today, but they're just not as formally specified. For instance, string, int, float, these are all immutable types. But we can also very easily create immutable references to normal objects. For instance here, I can say immutable person equals new person. And the reason we can do this is because we can look at this expression here and we can say, hey, the only things going into this expression are immutable values. String is immutable, 42, it's an int, that's immutable. The only thing here is immutable data, so why can't we just create an immutable value out of it? And this is not just limited to simple things. It flows all the way through our type system. We can even do complex collection initializer codes. We can look at arbitrary method calls. And as long as the only thing going in is immutable, we can take the thing out of it and make it immutable too. And I want to emphasize, person and list of t, we didn't do anything to these types to make them work here. It just flows naturally from the type system and the restrictions we have. Now, one other advantage we have is because we use immutable types so much through our system, we can actually freeze them at compile time. One of the things we looked at is, for instance, all of our static fields in Midori, they're forcibly immutable by the type system. At compile time, we evaluate these, create the object graph, and just burn the objects to read-only memory in the assembly. And this has a couple advantages. One, all of our static code is run at compile time, not at runtime. This means that all of that peanut butter cost that gets inserted into your C# code of whenever I access a type, is this the first time we've accessed a type? If so, run the static constructors, doesn't exist. That peanut butter cost is gone. It's all done at compile time. And the other great thing is we can actually share this read-only memory across multiple processes in the system. So it's not tying up. We have these giant immutable objects and statics. We can share them across all our assemblies. No worries at runtime. It's really efficient. So the last big system I want to cover is our error model. So this is kind of the primary motivation for our error model in System C#. When we look at this code, the first thing you'll notice is the code is conflating coding errors and recoverable errors. If you pass null to parse, you have a coding error. You have violated the contracts of the API, and your process needs to die now, not later. But we're using exceptions to model coding errors, which means that we've completely conflated, to the caller's perspective, what is a coding error and what is a runtime error. If you pass in 2 or 3 or 4, that's OK. We can recover from that, tell the user to enter something better. But once you start passing in null, your process needs to die. You have done something unrecoverable. The next thing is, if we look at the use cases of parse, when I'm looking at this method as a code reviewer, someone who's reviewing your code, you work on another team, I'm not 100% familiar with your API, which one of these statements is throwing? How do I know what is the control flow of your method? And the answer is you don't know. And the worst case is you don't even know if either of those things actually throw an exception. I've reviewed so much code in C# where people have just gotten paranoid about their UI loops and put try-catch everywhere with no rationalization for what they are catching. And also, right here, because we use exceptions for both cases, the caller has now taken a coding error where they've passed null and just said, oh, it's a recoverable error, return 0. They've taken a bug in their system and silently swallowed it. So our solution to this is, once again, is to encode this into our type system. Bake this in. First off, we fail fast on coding errors. Null refs, array index out of bounds, overflows, ooms, stack overflows, contract failures. We take the process down rudely. There is no way to interrupt this. The process dies fast, and it's very nice. And we also seek to minimize recoverable errors. Exceptions have their purpose in .NET, but we want them to be used for that purpose. We also want all error handling in System C# is explicit. The control flow around error handling is very visible to even the most casual reviewer of your code. And also, because we have all of this in place, it can give us all kind of static checking and warning about dead code in the system. We can get rid of try-catches which do nothing and have no purpose. The same with try-finalies. First off is we've added contracts directly into the language. And so we have two basic contracts, requires and ensures. Requires is our precondition, and ensures is our postcondition code. So these are, as you see here, syntactically, they're put at the top of the method between the method signature and the method statement. These are subtyping friendly. You can override them, and the compiler will require you to state that there are contracts on the base type that need to be enforced. And one of the other great things about our contracts is they are side effect free, provably. We use the permission system in System C# to enforce that anything you put in a contract or debug.assert or release.assert or things of that nature are side effect free. If you try to mutate in those operations, we will smack it down at the compiler. And this was actually one of the biggest impedences to us turning on both of these systems at the same time in Midori. When we turned it on, we had tons of code we found where people were mutating their state in debug-only code. And it was directly responsible for errors, timing errors that they were seeing in their release builds. And people pushed back on us saying, no, I'm not mutating, I'm not mutating. It's like, yes, this is why. And it was quite shocking in some cases, but now that we have it, it's great. And the other thing which is really great about this system is because they're side effect free, it gives our backend compiler a ton of flexibility. Our backend compiler, if it sees 10 calls in a row, which is just null check, null check, null check, null check, or assert valid, they can just hoist that to the top and kill the other 9 checks. And we've even found these are all enforced at runtime, these are all enforced even in release builds, and we found it doesn't add up to any real significant cost in our large-scale operations. So the other type of error we deal with are recoverable errors, exceptions, the cases where we do want to fail and recover from it. So by default, our methods can't throw. We have a non-throwing by default, and it's enforced by the compiler. And this is great because it allows us to emit error handling tables. We don't have to deal with a lot of the branching code that comes along with this. So it's much better code quality. If you do want to throw an exception, it requires opt-in from the caller and the callee. So first off, if you have a method which throws, you must explicitly state that it throws an exception. Otherwise, you get a compilation error. And once you've stated that this method throws an exception, it now becomes an error from the caller because the caller has not acknowledged that you will throw. And the caller must opt into this and explicitly state on the expression, I know this can throw. And what this does is this, at compile time, this doesn't translate down any code, but what it does is it gives us very explicit control flow annotations in our code base. We know exactly where the exceptions are coming from, and we can just at a glance know how the control flow changes. And once again, because this guy has declared, oh, I'm calling something which throws an exception, it also must annotate that it transitively throws an exception. So getting close to the end. So this has just been a broad overview of some of our more impactful features, but we have a ton of other work that we've done in the system. We have an async model similar to weights, which I'm hoping to sneak a slide in for. We have value type delegates in the system. So one source of heap allocation, gone. All our delegates are value types, and it's just much nicer. We have fast interface pointers, so this is a way of basically improving dispatch by holding on to the pointer and vtable as a joint pair. We have a couple of different versions of structs, primitive structs, which are provably reference-free, very nice for copying and blitting. Read-only structs, where you're basically enforcing that structs can never be mutable ever. So nice. As I said, we have immutable types like string, exception, int, float. It's encoded into the system, and these types just flow beautifully because they can never, under any circumstances, be mutated. We do have typed exceptions. Our error model does support it. So if we wanted to say that I throw, but only this type of exception over here, we do have support for that. I just didn't have time to throw that on a slide. We have lightweight enumeration. So when you enumerate in C#, there's a couple potential problems you run into. The first one is that it's double dispatch on interfaces. Every element you get out of an enumeration, you have to both call move next and current, which is a double dispatch interface call. We've whittled it down to more of a try get next. And the other problem is that whenever you enumerate, you're allocating an object. You've allocated that enumerator, and it's polluting the heap even though you probably just did a simple for loop, got some values out, but that process you have now polluted the heap. But with borrowed values and such, we can actually force that allocation onto the stack and not pollute the heap for simple enumeration costs. Really beneficial when you get into fun link queries. As a part of having destructible types, you do eventually force yourself down a hole where you have copy constructors for those. They're not the evil burden that C++ had. They're much more restricted and pretty much single-purpose guys. A lot easier to rationalize about. And on top of that, we have a whole, basically, equivalent of the BCL. We have our entire development kit with our base class libraries. They're installed separately, and we compile a lot of our projects directly against them instead of source. We have HTTP MDK, which is our equivalent of MSDN. Essentially, it shows you our base class libraries, our type system, talks a lot about system C# in there, and goes over that. And also, most of the time when you encounter a new language, you find a bunch of people that are like, hey, here's this great new language. I hope you like Vim and Notepad. No, we have full Visual Studio integration. Thanks to all the work the Roslyn team has done, we basically have a sub-branch in the Roslyn tree where we have a fork of the C# code base that we have ported to System C#. System C#, like I said, it's a back-compat preserving language, so adding more features to it is not terribly difficult. And so we have a full IDE experience on top of that. So you get syntax highlighting, IntelliSense, refactoring, the whole shebang. And as Roslyn gets better, so do we. It's really awesome. OK, good. So I do have time to go over the async model, which I was hoping for. I had to talk really fast. One of the things we did in Midori, like I said, one of our first features we did was the async model, which is very similar to C# async and awaits, except we call it awaits and await. And our basic model is, like I said, Midori is non-blocking. Any blocking call is always done through continuations and callbacks, and it's very explicit in our code. If your method can block, essentially it's going to do I/O or something of that nature, your method must be awaits. Awaits is saying, I have the potential to block on an unresolved promise or task of T. And calling any method, which block is also explicit. You must annotate it with await, saying, this is a potential point of interleaving in my code base. And likewise, if you have a synchronous method, you have a non-awaiting method, they are guaranteed to complete synchronously all the time. You cannot transition from a non-awaits method to an awaits method, because otherwise you'd be transferring from something that's non-blocking to blocking. In order to do that, you must explicitly spawn off a new task, which is doing that awaiting operation. Our main type for doing that is async factory, somewhat similar to a task scheduler in C#. And from a synchronous code base, we can spawn off a new task, or we can spawn off a whole bunch of different tasks if we feel like it. And one thing that's nice about our system is we actually, unlike C#, we don't use state machines in our awaits model. We started that way, and we kind of took it to as far as we could take it and decided it wasn't fast enough. And eventually, we decided to go with a link stacked approach. So we have one giant synchronous stack in Midori that's going up and down all the time. We know it never blocks, so we only need one of them. But every one of these run calls, which produces a new awaits, basically branches off an awaits call, we just create a lightweight coroutine link stack to run it all, which means that our code generation around awaits is really straightforward. When I call this await socket.connect method, there's no state machine there. There's no goo. It's just a bam, call that await method. It's a direct call. We do have a little bit of stack linking code in some places, but it's very minimal. In general, it's just a straight A to B call. Oh, yes. OK. And so here's a nice little slide where we've got a bunch of different features put together. So first off, if we look at the top, this is a basic sorting exercise. I have a delegate type comp, which is our basic compare delegate. I need to take two values and tell you which one is greater than the other. And so you can see as parameters, it takes readable values. And what this means is that delegate implementation, it can't mutate your values. You can't have this sorting method which goes through and says, I'm going to change this and cache it along the way. No. And also, we have a readable on the back end. And what that means is that not only can the delegate not mutate the parameters, it can't mutate anything that it captured when it was created as a lambda. It can't bind to a writable method on an object. This delegate is pure. It will only read things. It can never mutate state. Then we have our list type, which has two sorting functions to represent our main two compare types. comparer of t, which is just a nice little immutable base class, very similar to iComparable in .NET. And basically, first off, it's immutable, because compare should never be mutating state. You really need an immutable item here. And once again, its method takes two readable parameters. It can't mutate them. It can only return an int, which I typed as void, because yay. And what this means is, when we look at this foo.sort method, there's a couple of things. We immediately know this delegate right here, this lambda, can never mutate state. All it can do is read values. And because both of the inputs there are borrowed, because list doesn't need to hold on to a comparer, it just needs it for that function, and it's done. That means we can look and say, hey, why don't we just stack allocate that and be done with it? The list can't hold on to it. We're just using it as a lambda right here. So this sort method is provably side effect free. We know the sort will complete correctly. And we can take that lambda and allocate it on the stack no matter what you capture. So this is the code everyone writes today, and it just gets better. Like you said, C# developers do what they have always done, and their code is just better. And we keep them from doing bad things. So future plans. We're moving towards open sourcing the compiler. So first off, we kind of got to finish the language. A little bit of rounding the corners left to do in a few feature areas. And we also are going to finish the port to Roslyn because we want to build on top of what the C# team is doing around open sourcing in Roslyn. Right now, we've mostly got the parser done, and we've started in semantic analysis. Tons of work left to do, though. Online community has already expressed a bit of interest in our project. Some MVPs, the D designers actually contacted us about a paper we wrote a while ago, Mono guys, and continuing to collaborate with the C# team, share design reviews, feature transfers. We're actually planning on some of the features they're adopting. We're talking about maybe just doing them in their code base and then integrating them into ours later. So, and we're also planning on shipping in the box for Threshold. So we are conceptually Red Hawk v2 for those who know Red Hawk. And we're looking to ship at least 5 components written in system C#. So, and the way we're approaching this is our ahead of time compilation, as I said, we go to native. So we're trying to get down to native and make it so that the backend tools for the Windows team can't really differ between us and C++. All they care about is the backend binaries, and we're generating compatible code for that. We could just say, oh, we're going to target the CLR and go for it, but no. We want our native code. We want the code quality. In Threshold timeframe, it's going to be mostly us writing the code, but in Threshold +1, we're going to shift the burden of coding onto OSG and become much more like the C# team is today. And we're really looking forward to the feedback we're going to get from this process. So got a few minutes left if people have questions and answers, and yeah, we're hiring. It's a fabulous team. Paul was first. Oh, do we want to give them mics? Huh? No, it's just what do you mean? Oh, the syntax for destructor looks a lot like finalizers. Okay, so the question was, what do destructors look like in the type definitions? And the answer is they look a lot like finalizers. But in terms of the actual syntax, there's no... Yes, they run inline. We do not run them on the finalizer. And one of the beautiful things about it is because we have like a checked exception mechanism, we can verify your destructors don't throw. And we enforce that explicitly. Your destructors do not throw, and they cannot call awaits methods. No. Yeah, constructors can throw, but it's also an explicit thing. Constructors can await, and they can throw, but it's just another method call for us. We are having some debates on how we're going to handle destructible types and exceptions because it does create a question about destructors, but we haven't 100% resolved that yet, but we'll see. So is out-of-memory a recoverable exception? No. It is a runtime failure and your process dies. We have talked about if we move into lower section of Windows that we may have to make a recoverable exception, but that's still a design point. It's nothing that we've really firmed up what we would do there. But if we did, it would be specific to that layer of Windows. It would not be something that end users were dealing with. Mhm. 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 Okay. So the concrete one is, can you specify a region in which to allocate objects? At this time, no, you cannot allocate. You cannot say, hey, here's a region object, allocate into here. What you can say is, we are limited. I want this to exist no higher than this stack frame or no higher than my caller's stack frame. Yes, we have talked about adding explicit region support, and it's something on the table. But right now, we want to get more comfortable with the implicit model and then see if that will lead us to forcing our hand on an explicit model. Sure. Mhm. Extendable type systems, essentially? Yeah. We haven't really ventured down that path yet. We've talked a few times about it, but it's just never, we tend to be very solutions-based. Like, we are always solving a specific problem. And so far, that just hasn't been enough of one for us to invest time in. There we go.
Okay, I think we actually have to move on. The format is one that's brief, but the point is to get us exposed to a lot of topics, and then we have a whole year to delve deeper in a lot of these subjects on a monthly basis. So if there are things that in a particular talk that is really opens up a whole bunch of questions, I think that just makes it a fantastic thing to come back to in one of our regular TCN P-Lang meetings. Thank you, Jared.